Today we'll be covering aerospace failure investigations again. But today I have invited Mr. Thomas Brand, who is an investigative expert and has tremendous amount of experience in this arena. He's world renowned in this area, and I'm very privileged to have him over. Over 11 years as senior tech fellow at the Lockheed Martin Corporation, director and principal engineer, and lead investigator in multiple mishap investigations at the Aerospace Corporation, not counting all the ones he did at Lockheed Martin. 15 years as a chief technology officer, chairman for large nationally critical investigations, domestic and international service, and also an in-coast expert systems engineering professional. So Mr. Thomas Brand is an impressive individual, and I think we should all feel honored to have him here today. So with that said, we're going to step in right into questions. I also want to remind you that if you have questions, you can also put them in the chat. And if you do ask questions, you'll be rewarded, and I'll explain later how you'll be rewarded. So I'm trying to get you guys to participate. This is a very unique opportunity to have time from somebody that's quite busy. So Tom Brand, welcome. And if you can tell us a little bit more about yourself before we get started, in case I missed something that I think is important to cover.
Yeah, well, you covered the most basics of it. I think a lot of it boils down to it just means that I've been doing this for a long, long time. So no spring chicken.
Excellent.
Um, you know, I actually started with NASA a long time ago, 1979, as a biomedical research engineer, but then went to Lockheed, went the whole time before coming to aerospace. And aerospace was just a great opportunity. I started doing failure investigations at Lockheed when I was a senior fellow, all over for the corporation. And the neat thing about that is you get to see a little bit of everything, right? Every failure investigation is different. I did failure investigations for software, hardware, metallurgy, weird material properties, chemical properties, you name it, we did investigations. And when you're doing like something like that for the corporation, it's usually you're under the gun. I usually got called in when other failure investigations just flat failed to figure out what was going on, right? So these are billion-dollar programs, and you're just under a tremendous amount of pressure, and it's actually been just a really fun career.
That's amazing. And it's awesome too that they've had this vast experience, and hopefully our students today can really learn quite a bit from you. I want to ask the first question. We're going to start at the bottom, and the reason is because it bothers me every time I work on a design or assess a design, but nobody has ever thought of what failure modes could occur. And then later on, there's a failure, and people are trying to scramble through that. Could you tell us why that's so important? Why it's so important to conduct a failure modes effects and analysis? First, what is it? And then why it's so important?
Yeah, that's a really good point because you hate to get into a big failure investigation. Nobody's ever thought about this because you end up doing a bunch of almost negative work, right? So an FMEA is really, so you look at it two ways, and we're going to talk a little bit more about fault trees and fish bones, but you could look at an FMEA as I think they call it a bottoms up analysis, where a fault tree is the top down, where, bottom up, you're looking at it at a component level for the most part, and you're looking at how, if that component failed, how would the system react to it? I mean, as a designer, it's just super important to do an FMEA as you go along, because it makes you understand your design. You can see where your single point failures are. You can see how the system reacts to different failures. Now you can combine that with, statistical analysis for, how long parts normally survive. And you know that, hey, we know I have a part that's got a very short life on it. So, that one's more important. Or maybe you have failures of parts that we know historically don't fail very often, so you're less concerned about them. But it really just helps you flush out your design so that you truly understand it. Now, when you get into a failure investigation, it's equally important because but now you're doing a top-down investigation where you're starting at a failure and trying to work down to a component, usually a system failure, work it down to subsystems and failures. But now you can pull up that FMEA and you can go through. When you start getting down to the component level, it's always good, review your FMEA and see, well, what were some of the effects of some of these parts failures? And now you could start making a correlation between that and what kind of effects you're seeing during your investigation. It just gives you a little bit more focus, because you're going to end up doing that anyway.
Yeah,
So,
right.
as you get down to the component, so if you already have it to begin with, it just allows you to work through it faster. It starts, the whole thing about investigations is to try to see correlations between what appears to a lot of people to be effects that don't have anything to do with each other. You have to start seeing patterns in the effects, and FMEA helps you see that, just like the, top-down fault tree. It all starts coming together. But, even more importantly, even if you don't have a failure investigation, doing an FMEA as a designer, um, on complex systems, you just have to really do it, to really understand your design, how the design works, where the failures are, and can you stand those failures?
That's
Uh,
awesome. I completely agree. I mean, sometimes designers are very myopic about the
mhm.
design, but when they do a failure modes effects and analysis, it opens a whole realm of failure modes that they did not consider, that could then lead to a better design when they implement better design practices. I really appreciate that perspective there. Now,
That's
you've been involved in many failure investigations.
many, yes.
So and why do failures generally occur in aerospace systems? Are the issues connected to technical, cultural, or combination? Some of the ones we discussed in this course include the Challenger and the Columbia shuttle investigation,
Yeah.
and the investigation reports and the boards involved in that found that was just not technical but also cultural. So, just want to get your perspective on that, because you've seen so much. So I want to see what your thoughts are on that.
So, I think probably 90% of the time, failures are due to lapses in system engineering. We said that time and time again. We're seeing that right now with the advent of all these, I'll call them young rocket companies, going out there and trying to launch their rockets. They just, system engineering discipline, test like you fly type disciplines, which is all part of systems engineering, um, is just, that's where we see most of the lapses. And how do we go into that? If you talk about Columbia and type shuttle accidents, so maybe we should talk, actually, Vinay, can we talk root cause and direct cause, and that would lead right, I think,
You
right
you you
into that.
you're free to talk. I'm
Okay.
just honored to have you here. So feel free to take it wherever your heart takes you. So
Okay, so let's do it that way, and we'll back into it a little bit, because I think it's so important for people to understand direct cause versus root cause versus um, contributing cause. And everybody uses a little bit different terminology. That's the terminology I use. That's what I've kind of, that terminology is mostly close to how NASA does investigations. When I first started doing this, we, Lockheed used a different one, NASA used a different one. And as we started doing more investigations, me and my team kind of adopted our own, and most of it is based on NASA. Um, so, a direct cause, when we do an investigation, for the most part, we're looking for a direct cause. And direct cause means what happened to cause that failure. Um, for instance, a engine shut off on a rocket. The direct cause, and let's just say because the main propellant valve closed, um, you finally get down to the point where you discovered that, hey, the main propellant valve closed. Maybe it's because of an electrical issue or something, but that's a direct cause. And a direct cause means that it's something that, if that item happened all in by itself, it would cause the anomaly. So that's what a direct cause is. So you can actually have investigation where you end up coming with two or three direct causes, because sometimes they're collateral events. So you might get two or three causes, and you can never determine which one came first because sometimes these things are happening in milliseconds. Um, so you end up with several direct causes. Now, a contributing cause is even a lower level. A contributing cause, and we see this on anomaly investigations all the time. Something broke on the rocket, and maybe it had nothing to do with the anomaly itself, but telemetry showed something was not working right. And that's really a contributing cause where if it happened all in itself, it would not cause the anomaly. But you get enough contributing causes, and because of collateral type damage from contributing causes, you could end up getting a direct cause. Now, root cause, that's really harder. Now, a lot of people will do an investigation. They say, yeah, we found this valve failed. That's root cause. And that's really not true at all. Root cause is when you take it that step further. Okay, why did the valve fail? Did we not ATP it correctly? Did we not qualify it directly? Was our qualification boundaries incorrect? Um, was the
And
environment?
just for the
Oh,
audience,
okay.
ATP means acceptance testing. So
Oh,
what we talked about in class about when you
sorry.
manufacture something, you have to prove it out. Go
Right.
ahead. Sorry.
Yep, no, it's true. And qualification, everything always goes through a qualification test, which is always, some X amount of dB above your standard ATP or acceptance test. And so these things could be wrong, or maybe somebody screwed up in the factory when they built the valve. You go all the way back to find out what really caused it. You try to get to the actual root cause all the way back to possibly management, and that's where you come into like the shuttle investigations. So the shuttle investigations, of course, had um, definite hardware issues. In one case, the tiles were disrupted, and in the first case, it was an O-ring because of temperatures. So they got to direct cause. They said, look, because of a tile came off on launch, hit the leading edge of the wing, made a hole in it, and that's what caused the heat shield to be compromised. Um, in the other case, an O-ring, they launched at a low temperature and actually a temperature underneath their lower temperature bounds, and O-ring got compromised. But what truly led to those failures was management. That was schedule was king on the shuttle program. I don't know if any of you worked the shuttle program at all, but schedule was everything on the shuttle, and they were under tremendous pressure to launch the shuttle. It was actually ridiculous. I helped with a couple of payloads on a shuttle, and it was like the shuttle would go, we're launching, in 3 weeks, whether you're ready or not. You're going, well, wait a minute, you're launching this for our payload. So they were under tremendous pressure, and that's what ultimately caused both of those issues. They did um, I forget what they call it now. They call it it's a type of root cause analysis where it looks into organizational issues that was really developed because of the Apollo and shuttle issues by NASA. And what they discovered was the true root cause was schedule pressure, management. It was the pressure to launch at all risks and to take risks. What's interesting about the first shuttle they lost, the final report came out and said that this was really management just being pressured to launching, and they did it, ignoring things. The second shuttle, which is that was the Columbia, right? The second one, yeah. Um,
And in
NASA came out the exact same result.
and in both of those cases, not only management was to blame, but also engineers because they're oversimplifying the message in PowerPoints. I think
Yes.
one of the points I made was that engineers were dumbing the message down so much that the message was not coming clear. So, what do you think about engineers communicating clearly as well? even if their career is at stake, even if you have to say something nobody wants to hear.
So that's a really good point. I mean, as an engineer, you're ultimately responsible for this, and you have to be. What I see on the management side, though, and I've seen this recently at another contractor, that um, management has to, how do I put it? Engineers take after what management does. So when you have engineering management, and if you see that engineering management is letting things slide under the table, and engineers see this, especially young engineers, because they're just trying to learn the ropes, and um, if they see engineering management not taking things like engineering review boards seriously, very little shallow information, then that they understand that, hey, I don't have to put 100 hours into uh, an ERB presentation. I can put 5 hours, make it a 30,000 foot level, and they all seem to be happy with it. So it flows both directions. Engineers at the lower levels um, have to send the right message up. Messaging is very important, but it's just as important, if not more important, for the chief engineers and the leads on these programs to set the example, because everybody's watching them, because they're trying to understand where the boundaries are.
Talking about a little bit more about that, because will you agree that integrity and honesty starts early in school, later in your career, and even when you're in operational programs? How important is integrity to really making sure we don't get all these failures? And when I talk about integrity, is cutting corners, not doing due diligence, and also doing things fast to get that one award that you want to get, or a raise you want to get. Can you talk about that a little bit from the
Yeah,
career, from your career?
it's a really good point, and it's a fine line, between, I'll say, cutting corners and, say, doing the a really good job, because some of these programs operate so rapidly. You're under so much pressure to do things that you don't even realize that you're cutting corners. And that's where the engineering team has to get together, not just the chief engineers, but the engineering team and the peers. Everything should be peer reviewed, and the peers have to check each other and say, hey, I don't think we're putting enough effort into this particular item. So everybody kind of sits back and goes, oh, yeah, we really have to do that. So it's a tricky balance. Um, you talk about, there was a contractor that lost a couple rockets, and what they didn't understand was this very thing. They're rushing really fast because they didn't care about the success rate that much. In fact, they advertised what we would call a really bad success rate, but they were selling rockets very cheap. Um, and customers understood that until they lost a couple of them. And then the one thing the customers said was, well, the satellites are very expensive. Let's get right down to it. Satellites, on the whole, are way more expensive than it costs to launch a rocket. Everybody says you got to get rocket costs down cheap, 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 so that we can launch more, more, more. For the most part, what I've seen is that's all BS. Um, the satellites, even on the commercial side, are so much more expensive than what it costs to launch it. Um, that you just well, they rushed. I'll say, well, let's get back to the story. They rushed, and then their people they were selling the rides on started to say, wait a minute, you didn't tell us we could lose our satellite. It's taken us a couple of years to build this and cost us tens of millions of dollars. And I think their reaction was, well, we said we're giving you um, a cheaper price because the probability is lower. And they said, oh, well, we never equated a cheaper price to actually losing our asset. So customers lost faith in them. Their employees, their morale was terrible. Um, and shareholders, lost faith in the company. So they really said, wow, we didn't truly understand the cost of failure. So very eye opening for them.
Yeah, that's excellent. Now let me ask you this question. A failure occurs, maybe an aircraft crash incident or a rocket failure or satellite failure. Um, what are those very first steps that need to be taken not to contaminate the site, making sure we're keeping everything secure so that we're not tainting the investigation. Can you talk a little bit about that and the
Yeah,
importance of developing timelines?
yeah, it's very important. And, all contractors, all companies have, investigative plans in place for when things like this happen. You have to. Of course, if you're flying under an FAA contract to fly a booster, you're required to have a mishap investigation plan. And that plan has to have a lot of things in it. One of the first things is uh, you put together a very small team immediately and you cordon off the area. You lock down all resources. You take all the digital data off any computers. You have people write statements, witness statements of what they saw, and you have them do that immediately because people forget very quickly, right? Just have them jot it down, no matter what they want to say. And this is not to go to a court of law. This is for the investigation team to, try to sort through it. But you really need to not touch any of the hardware until the plan is in place so that you can touch it correctly, right? So you can see exactly where it is. It's typical for a rocket. They would identify where all the pieces are. They would take a geolocation stamp for every piece. They would take multiple pictures of each piece where it's at before they ever take the piece out of the field. Then you take the piece out of the field, but you have a full map of where it's at. And it's so important because we have on rocket launches, we've been able to get down to direct cause because of pieces they found. If you're lucky enough that the pieces fell on the ground, but yeah, very, very, very important to keep it, catalog it. I mean, it's really just a big bookkeeping task, but you need to do that so you can start having metallurgists look at all the pieces and really try to figure out what's going on. But you got to be careful. You don't want to disturb it. If you're going to have a metallurgist look at something, you don't want to mess it up. You don't want to contaminate it because maybe now you're looking at putting it under electron microscope and seeing what kind of elements are all over the piece, and you don't want to be adding things to that. It's forensics.
It's forensics investigation. Can
It
you
is.
tell us a little bit about the importance of developing an accurate timelines and the things that can go wrong when it comes to telemetry, data acquisition systems,
Mm.
and delays, and also sampling rates? Can you tell us a little bit about that?
Yeah, that's a great question. I can't say enough about developing a timeline. That's one of the very first things an investigative team starts to do. You start to put together an investigative timeline, or I'll say an anomaly timeline. And this has to be very exact. So, you know, you you try to do that timeline to the best of your ability of your highest telemetry rate. So it could be down to the microsecond or milliseconds a lot of times. If you can get down to microseconds, you're really doing well. But because sometimes four or five things happen and they happen very quickly. Maybe they happen within 100 millisecond time window. What you're really trying to determine is, okay, which item happened first? Was four of those items that happened collateral damage, and we really had one thing that happened, or were there two things that happened? Because it's not uncommon to have more than one failure, especially on a rocket, especially on new rockets, to happen simultaneously. But taking that whole timeline um, is so important of trying to correlate it to the data and correlate it with what you see on film. I say film, video. Um, we take those videos frame by frame. We try to correlate it to a timeline. We correlate it to um, a gyro data, accelerometer data that you see on the vehicle, possibly from the IMU, or a lot of times, launch vehicles fly different types of accelerometers. Look for current traces. current trace is very super important. And so we're just looking for, what are those effects and what came first? Hey, we saw some effect on a video, and oh, hey, look, that correlates to a big shock that we saw on an IMU. So okay, that could be any number of things. Could be an explosive event. Um, and we see something else that's a very small indication. We see a current indication, go, wow, what could have caused that current indication? And maybe you discover that, oh, some valve opened when it wasn't supposed to open. And we saw that in the current trace. So it's just, you know, very important to get that timeline down as best as you can as you go through. It helps you weed out what's. Remember, an investigation, especially when something blows up, as soon as it starts blowing up, all kinds of things are failing. And you need to try to figure out, well, what happened first, and that's where the timeline comes in. Does the timeline make sense for the particular failure that you believe is the direct cause? And this can be a challenge because telemetry, a lot of times, the more you fly, I don't know if people realize that, when you do a developmental rocket, you have lots of telemetry, but maybe it's focused in certain places. Maybe it's focused in accelerometers because you're looking for the maximum expected environments that the rocket's going to see while it launches. But as you progress through and become operational, maybe you don't take telemetry off, but now you use that bandwidth for your payload and for other things. But because of that, when you have mishap investigations, sometimes your telemetry is not all that great. It's kind of slow. IMU data is not super fast. I mean, it's typically 60 to 300 hertz, which isn't a lot when things start exploding. Um, Telemetry timing is super important. We've had vehicles where they discovered after the fact that their telemetry timing was all off. And we had a heck of a time trying to figure out what is the true timeline of things that happened. And that's when it'll come to things like movies, and when you start going, okay, we're going to correlate everything to first motion on the vehicle. And we get first motion by an accelerometer or an IMU saying we have first motion. And then from that on, we say, okay, we're going to call that gospel and try to correlate the telemetry in. And it's even worse when you have two or three different telemetry sources, two or three different packages. We had one contractor that had RF telemetry, but they also had telemetry, high-speed telemetry that they recorded onto solid-state drives on the vehicle that didn't get recorded because it was all high-speed data, but they could use, like if there was a mishap. Well, it turned out that didn't correlate to any of the times for the RF data. So tons of effort. And it actually took, timing experts a couple months to finally get all this data to correlate to each other. And so that's a big lesson learned for people that, be sure that, you need to assume that something's going to happen. And if something's going to happen, think about, well, what kind of data am I going to need? And does the data that we have even actually make sense? You can do tests to see, hey, is the timing of this data really correctly? Because you look at it on your screen, but you're not trying to really correlate it with anything. It's not until you have like a mishap that everybody's putting data from different sources on top of each other and trying to make sense of it when they discover, wow, somebody didn't set the clock on this other piece of equipment correctly, and now everything is just it's a mess.
That's awesome, Tom. Can you tell us a little more about the timeline? So there'll be signatures in telemetry. How do I know if those signatures in the telemetry make sense or not? Is that based on analysis, flight experience, qualification? Like, what am I using as my basis to know if what I'm seeing makes sense?
Oh, that's a really great question because what we see a lot is, first of all, a contractor should have analyzed all their telemetry to begin with. You do Monte Carlos, try to figure out what the telemetry, like the trajectory is, and all of that. But if you've flown multiple times, what you need to do is go back and compare your flight to past flights. So you really want to look at your data. How did it compare to last flight? how did it compare to the maximum values that we predicted for these particular telemetry items? And even more importantly, how did it compare in family? That's a really important distinction. And we see this with contractors all the time. We ask them, well, is the data in family? And they'll go, well, yeah, it was completely within spec. No, that's not what we asked. We understand that data was within spec, but look, you had 4 flights that say the data was at, say, 2 volts, a real simple example. Um, but the requirement was it has to be between 1 and 5 volts. They said, hey, look, it's within the requirement, but the past 4 flights has been 2 volts, and this one was 3 volts. It may be within requirements, but it's out of family. Why is it different than all your other flights? I understand it's within the requirement, and it just turns out that for the most part, things don't vary that much. Now, we have seen data where every single flight is kind of all over the place, always within bounds. But typically, what you'll see is in past flights, the data will lay right on top of each other. And so when you see something that's even off by a little bit, what is it? We had one, and it was a pressure reading, and we had one of our engine experts on this investigation, and this little pressure bump, and they were getting close to trying to finalize the investigation. They think they knew what happened, and he kept going back, well, what is this little pressure bump? I said, well, we don't know what it is, but it's well within spec. He says, but we never saw that on any other flights. What is the bump? And he just wouldn't leave it alone. And it turned out to be a key piece of evidence. It was actually a small pressure bump that proved that propellant was actually boiling and causing some cavitation on the input to the pump. And turned out to be a key piece of information that actually let everything else come together. So
So a little blip led to the answer.
it did. A little blip
Wow,
that was within requirements.
amazing.
Right.
Is it always important to get to the bottom of things, or is there a way to somehow implement corrective actions? If you can get to the bottom of it, perhaps implementing corrective actions for most of the things you think happened
Yeah.
and see what happens. Could you talk about
Yeah.
that?
Yeah, exactly. So I did a big international MDA investigation that we never got to, I'll say, root cause. What we got to is we ended up with 9 possible direct causes. I mean, we literally had 2 pieces of like 30 hertz telemetry that we analyzed for like 6 months. And it's amazing the information we got out of these crummy little pieces of information. But we finally got it down to where we knew the component that failed for sure. We proved it in test that component would fail in the failure modes that we saw. That's also super important that we haven't talked about. Um, but within that component, there was many subcomponents, and we ended up with 9 possible direct causes within that. Um, and so we ended up doing corrective action for all of them because we couldn't prove which one it was. So we had to take a very blanket uh, corrective action for every single one of them. So that's what you would typically do. If you're not sure which direct cause truly caused it, then you go take corrective action. And what most contractors will do is you find things called, I talked about in contributing causes, you'll find direct causes, and you'll find observations. Hey, I had a data observation. Normally, of course, you always take corrective action for direct cause. You normally always take corrective action for contributing causes, and you might take corrective action for observations. So
That's awesome. Thank you, Tom. I have a few more questions if you don't mind. Is it okay with timing, or should we postpone?
I'm fine with timing.
Okay, great. Thank you for your time. I know you're pretty busy. Can you tell us a little bit from your experience in working countless of investigations to describe the difference between fishbone, fault tree, the 5 whys, And which of these investigative methods you prefer, which maybe you don't prefer one or the other, but maybe you can describe advantages versus disadvantages and let our audience decide.
Yeah, that's a great question too, because it's I've helped with investigations that people are just adamant fish bones are the holy grail, and I use fault trees, and that's my favorite. Um, and for me, um, I'm kind of a visual person, and I like to see all the data laid out logically in front of me. And for me, a fault tree is just a logical way to look at it, where you have the fault on top and you can see how the fault rippled through different subsystems down to the component. And I can kind of look at that and just make correlations between what we see. Um, Five whys, a lot of people use it, nothing wrong with it, but that's actually not too much different than a fault tree. I still think you need a fault tree even to do a five whys. It just, five whys just means that, this broke and you ask why. Say it broke because it ran out of fuel. Why? Well, it ran out of fuel because the valve closed. Why? And you go like five levels deep. And I mean, the reality of it is five levels might not be enough. I mean, you really need to ask why until you get down to the actual direct cause. Um, I think probabilistically, they kind of people kind of believe that if you go five layers deep, you're kind of there. And that's true for probably 90% of the time, but sometimes you actually have to go deeper than the five whys. So nothing wrong with the five whys. Nothing wrong with fish bones. There's a lot of people that like them. I like fault trees, but let me tell you, these are just tools. Um, I've heard people say that you have to have this because it's going to lead you to the solution. I've never seen that in my career. Um, it's just a tool. The one thing you have to do in an investigation is be very thorough. Keep track of exactly what you've done so that you don't repeat yourself. And that's where things like fault trees, really help you. It just helps you keep track of exactly what you're doing. When you go in to do testing, because remember, you got a lot of people. I mean, the one I kind of mentioned with the MDA, we had 50 engineers, working for 9 months, full time, over full time, to finally get to that investigation. This is a lot of money. Lots of testing got done. So you want to be very thorough and you want to figure out your test program. And what's your test program going to do? Your test program is going to try to validate like fault tree blocks. If you're not validating a fault tree block with a test that you're running, why are you running the test? And if you say, well, I think I'm running the test because of this and this, you go, well, did we miss something on the fault tree? And maybe you did. So you need to look at that, but you always have to correlate back to it. So, you use that fault tree as the main encyclopedia of how you're doing the rest of it. So your testing gotta correlate back to a fault tree block. This is how you're justifying doing that testing. When you're doing that testing, you better have a test plan, very exacting test plan. Need to show why you're doing the test. What are the test like you fly exceptions? What are you truly going to learn for it? How does it differ from what happened on the launch vehicle when it exploded? Was it the same environment? Are you testing in a vacuum, not a vacuum? Are you testing at the right temperature? Somebody will say, yeah, we tested at liquid nitrogen. You go, but there was no liquid nitrogen on the vehicle. Your liquid methane or liquid oxygen, which is different temperature regimes. So all these things you have to look at. So you have to and document that very exactly. So when you end up with a 8-month investigation and you end up with 40 tests, you can go back over and look at them and say, wow, what test? I want to do this test. I think we already did that test. Go look exactly what you did. So it's very important to be methodical. And I think whichever system you use, I think you just have to use it the best you can, document it well. Um, Definitely, I just can't say it enough. Document, 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 because you really do have to be a really good note keeper because you want to move forward. You don't want to move sideways and then discover that, wow, we covered that a month ago. Well, let's not do something twice. Just,
And this systematic approaches of documentation is extremely important because you don't want to bias the investigation, correct, Tom? Like everybody will have a pit theory about what could have happened. They may have their own opinions, but at the end of the day, you have to do your due diligence, correct?
you have to do your due diligence. Exactly. And so this is where a lot of pressure comes in, right? Especially when investigations go on for a long time and you're going to start getting pressure from upper management of, wow, you need to come to root cause. This is costing us a lot of money. But you kind of almost have to ignore that and say, well, we have to do the due diligence. You have to go through it. Um, Otherwise, it could just fail again. And we've seen this happen. It hasn't happened on my investigations, but we saw, back in the 80s, two big titans that went off. And the first investigation did what they thought was a thorough fault investigation, came up with root cause, did a corrective action, and they lost another titan. Exact same thing. And they did an investigation and discovered that, oh, we were wrong in the first investigation. Yeah, so that's where
That's
people get pressured.
that's awesome. And we discussed in class how a satellite from a particular company failed 3 times due to the same failure mode over and over and over. One of the things we learned in class is do not forget the lesson, right?
Don't forget the lesson.
Yeah.
It's
So
absolutely
so
true.
how important it is, um, one of the things that we do in investigations sometimes is to develop an end-to-end scenario where elements of the fishbone and fault tree can be threaded into that scenario. Can you tell us a little bit about that and whether that approach has been used or employed?
Yeah, and it's a good point. You have to at some point during the investigation, you have to start coming up with scenarios. And what the scenario is looking at your timeline. Um, the very important timeline is to try to figure out, you try to lay out, here's what could have happened. This could have failed at this time, causing this to fail, causing this, causing the ultimate demise of the rocket. These are scenarios, and sometimes at some point you'll come up with two or three scenarios because you're not sure which one. And so this is going to help you start focusing. Now, those don't happen till, I'll say, pretty far downstream when you've already gathered a lot of investigative evidence. But the scenarios are oh so important because when you finally come to root cause, well, you better have a scenario that fits fits that direct cause. If you can't explain what happened every millisecond until it exploded, then you could be wrong. Um, and this is where people like the MDA come in. MDA probably has the best mishap investigation process of anybody out there. They are just very orchestrated, and you cannot declare direct cause with them unless you've gone in the lab and reproduced the failure on the ground. If you can't reproduce the failure on the ground, they don't let you call it direct cause. Now, you might not ever be able to reproduce the failure, but you better try to come up with several direct causes to take corrective action on. Very big on test, and totally agree with that. Totally
And and
agree.
and, and that's a very tall order. Um,
It's very tall order.
Let me ask you this, and this is the final question, followed by a few more, if you don't mind, related to career advice, and then we'll move on to the audience and see if there's any questions there.
Okay.
So with this final question, we'll move to career advice, but the final question there is, you have to evaluate elements of the fishbone and fall tree in a failure investigation that could be multi-billion-dollar type, system. And so the question is how you balance, and first, how you develop the refuting evidence, how you develop the supporting evidence, and how you balance the refuting evidence against the supporting evidence to come up with a credibility rating that could go from most likely to unlikely, or most credible to unlikely, for example, or
Yeah.
not credible at all. Could you help us guide us through that question a little bit?
Yeah, that's when you start getting into adjudicating like that, that is tricky. It's really important. This is just a logical sense that you go through. Um, you're trying to adjudicate a failure or just um, or not adjudicate a failure. And again, you're trying to think of it that way. You say, well, if you're trying to refute, so you say, you have a bone that says valve A didn't close. Well, what's the refuting evidence that says that it closed? Um, and then what's the evidence that shows it didn't close? So you're almost trying to argue with yourself of, hey, look, I have a lot of evidence that says this valve worked, but look, I have telemetry that if we work that telemetry backwards and we're looking at pressures, say that the valve um, now I almost get myself backwards. The valve did work. So you kind of have to balance those against each other. But that's all part of the process. So I mean, trying to refute something is really, um, I think, part of your just logical process of thinking about it, because you go, well, let's prove that the valve um, closed like it was supposed to. Well, on the converse of that, let's prove that the valve didn't close, because maybe you go through and you prove that the valve must have closed. But then somebody comes up with some evidence and says, but look at this evidence. It doesn't appear that the valve closed. So, it's just almost another dimension of doing the failure investigation. Of It keeps you not so focused um, on a way of, you're not looking for the answer, right? Hey, I'm trying to prove that this valve closed, and so I'm just going to cherry pick the data to show that the valve didn't close. But on the other hand, now you have to look at it the other direction. Well, did it close? So it just helps you kind of get perspective. Make sure that you're correct, and you say, and how do you adjudicate between the two? Uh, you know, That's a great question. I don't know if I can answer that just off the top of my head.
Well, I mean, I
But
think you did. I mean, basically,
okay,
you're playing lawyer against yourself,
you do.
looking at the problem on both sides of the fence. And if you have a lot more supporting and no evidence, no refuting, you're probably most credible. If you have some refuting versus supporting, you basically balance the evidence, right? Is what you're
You
saying.
do, because people they get myopic. And I'll give you kind of a perfect example of that. It's a simple one, but it had to do with a tin whiskers and a certain component. Well, they went and looked at, this component could have been plated at two different manufacturers, and the group, and I wasn't part of this group, but I was on the management team that this group reported to. They went to both of them and they said, hey, this contractor, wow, their procedures are super great and they're wonderful. We love them. This contractor, their procedures are shitty. And we just don't think they know what they're doing. So we're pretty convinced that they screwed up the plating process. And they kept focusing the investigation on this contractor. And, my thing was, I actually used I'll say the crummy contractor many, many times in my career, and I never had a problem with them. And so, I'm kind of going, well, but do you have any proof that they screwed the procedures up? No, but they're just not disorganized. So that must have been it. But you have no proof.
Yeah.
Um, and
So,
they kept at it. In the end, it turned out not to be that contractor at all. It turned out to be the warehouse that
okay.
messed up taking old parts from years before and putting them in with the newer parts that were supposed to be 10 free. So, they just got so focused because they said, these people, we just don't like how they do business. So it must have been them.
Yeah. And do you think in these investigations, there could be some integrity issues where people know that it could have been their fault, but they're quiet because they could get fired, or they feel that they could get fired? Maybe in the
It's
technician on the floor or some engineer.
Yeah, it's possible. I've actually never really run into that, to be honest with
Okay.
you. I could see that it could happen, but I have not really. Maybe I've just lucked out. Haven't really seen that. People have been very open to, whether they screwed up or not. And
Yeah.
it's better for you as an engineer to just, you know, say that you screwed up. And I always tell engineers, say that you screwed up and tell us and we'll fix it. And all sins are forgiven. Now, you better not make the same error twice, or or we're
Yeah,
gonna have a little talk with you.
yeah. That takes me to your the next question here. If you have career advice to engineers, and we have working students, but we also have undergrads and graduate students. If you have career advice for the students today, can you give us some career advice here?
Yeah, that's a good one because see, I feel this is the one thing I like about anomaly investigations is you see every discipline. And I think my biggest career advice is when people get pushed into something that's out of their comfort zone or swim lanes, that you need to embrace it. If you're a mechanical engineer and let's say you get put on an investigation or something else that has electrical, don't shy away from it. Um, learn about that topic. Um, and this not only goes for anomaly investigations, but it goes for anything. When you're put in charge of something, don't ever think because hey, I'm a mechanical and this is an electrical problem on this design, so I'm going to get an electrical engineer and I'm not even going to look at it any further because I got an electrical looking at it. That's the wrong attitude. You have to you look at everything and learn about it. It's a great learning opportunity, whether it's investigation or just design. Now, I'm not saying you shouldn't bring the electrical engineer in. You absolutely should. But you embrace it. Learn as much about it as you can. Take me, for instance, I'm educated as an electrical engineer, um, but I probably know more about metallurgy than most people. About heat treating, I know a lot about heat treating, done a lot of heat treating studies with NASA. I've done weird chemical anomaly investigations. I sat in uh, with NASA at White Sands in a lab for nitrogen tetroxide out in the middle of the desert for a week doing experiments with a head NASA chemist. Um, and it was very eye-opening for me. It was great. I learned a lot, and we ended up finding out what was wrong, and the chemist couldn't figure it out either. But it was one of these things where you do enough data and you set the data out in front of you and you sit there and stare at it for a couple hours. And we said, whoa, it just came to us. Here's what the problem is. Weird chemical properties, said software, hardware, of course, electronics, spice analysis, done them all. And I think you just don't shy away from it because this is where you're going to put yourself above everybody else. When they see that you're really versatile, and it's not that they're asking you to design something outside your field, but you're not afraid to take part in it. You're not afraid to help, or maybe you're the lead, but you can end up talking about the subject, talk about it intelligently, and I think that's probably the biggest advice I give to people. Like, just because you're mechanical, don't shy away from the mechanical stuff. If you're a stress engineer, don't shy away from the metallurgical part. These are all just learning experiences. And if you learn it all, pretty soon people will start going to you because they'll forget. They don't even know who you are anymore. They'll just go, I know when we give this, person um, something to do that they do it. And whether it's mechanical or electrical or software. But yeah, that's probably my advice.
So basically, be a learner, or be a learner is
Be a
what I'm
learner.
hearing. Yeah.
Absolutely. Be a learner.
So now, go ahead.
I was just wondering, how often do you find issues with components that like failed or something that didn't actually have any cause or effect on the overall like direct failure or root cause? And then when you find those, what do you typically do about that?
Mm. Yeah, that's kind of what I was mentioning, like contributing causes. Um, all the time. I don't think almost any launch vehicle ever launches where we go back and look at telemetry and the after the fact that we see weird little things happening. maybe something breaks. Could be electrical component, could be a mechanical, but it wasn't in a system that caused a full failure. Then you do corrective actions on those, and especially in a big failure, you end up with typically a lot of things going wrong simultaneously. And obviously, if you can't sort them out, you definitely have to take corrective actions. But I don't know. Did that answer your question?
Yeah, thank you.
Okay.
How 90% of the failures that you see are due to lapses in systems engineering.
Yes.
I was wondering what advice you would give to systems engineers and what issues you see within systems engineering specifically, not necessarily just management, that
Sure.
could be contributing to that anomaly.
Yes, so wow, this is a good question. And I could talk about this particular question all night long. Because when I started at Lockheed, I started in Sunnyvale at Lockheed Missile and Space Company. We actually had system engineering groups. This was in the 80s. Nobody had this sort of thing. And I've seen a change in systems engineering pretty radical since then. And for the most part, not in a good way. I think to be a really good system engineer, a lot of people look at system engineering and they don't want to do it because they say, well, that's just all requirements and um, mostly requirements. They take care of requirements, test requirements, but I don't see it that way. I think systems engineers should be looking at designs. They should be redoing analysis, almost like a IV&V, if you know what that is, independent verification and validation. Um, and and we used to do this all the time. Design would come to us, and we would redo a lot of times stress analysis. We do pressure calculations, and we'd find problems with it within the system engineering group. And I think that's the biggest problem I see nowadays, where they think systems engineering is really the requirements, but it shouldn't be. Uh, I'll say at Lockheed, system engineering ran the programs. They ran the design programs because those requirements were super critical, and they had to make sure that was it really doing what it was supposed to be doing, and they backed that up by engineers doing their own analysis within the system engineering group. And again, I see people getting away from that. I see chief engineers nowadays are people that just run the risk group, run the requirements group, and show them what it's all about. Now, don't get me wrong, requirements are so critical, and people write such terrible requirements. It's real art, but so that's super important. But I think system engineering has to take a much more active role. I think programs that do better are when the system engineering has a bigger vote than, I'll say, the design engineering, because when they see something going wrong, they can stop the process. And I don't see that enough anymore.
Well, excellent. Thank you so much, Tom. I really appreciate the time that you spent with us. It's double the time that I was expecting, so really appreciate your time here. I'm very, very honored to have you here. Thank you so much.
No, thank you. I mean,
I-
I
If
love
you
to
have
talk about
some,
this stuff.
yeah. Do you have any final thoughts? Otherwise, we will conclude.
Yeah, I think you're in a wonderful field. Just don't be afraid to go outside your comfort zone at all. People, you go outside your comfort zone, you will step up to it, and you'll become more comfortable with it. So people always step up when they're given something. I've had a couple times in my career where they gave me assignments and I said, "Whoa, I don't think I can do that." And they said, "No, you're going to do it. Just go do it." And they ended up turning out great. And so it also took good bosses to understand potential and say, "No, go do this." And you just go do it. And I think it's super important that always look to learn. And if something's outside your comfort zone, it means you have something to learn about.
Okay. Thank you so much, Tom. That's amazing. What we're gonna do now,